So reminders to get started. Homework 4 is available on Canvas. Been there for a few days now. And this is all about computational learning theory. And it, if you've seen it already, it's all math, no coding. So for some people, you'll find that this homework is extremely easy and you'll feel this is not a waste of your time. Some people will find the exact opposite. You probably know where you are on that spectrum. So, if you think it's very easy, I would say start soon, get it done. If you think it's going to be hard, I would say start soon because you want to kind of let it simmer. So either way, start soon. There's some discussion that's already there on Piazza, I think, and keep that discussion growing. Use office hours, etc. The other announcement is about Thursday's lecture. It's going to be a slight difference from our usual program. It's going to be a tutorial that Purvid and Oliver are going to do on using practical machine learning tools. In particular, we'll be focusing on scikit-learn. Scikit-learn is a popular Python library for machine learning. And pretty much anything in machine learning that does not involve neural networks, I would recommend using scikit-learn. For anything that does involve neural networks, I would say PyTorch or TensorFlow. So we'll be doing a tutorial on scikit-learn, which has tools for things like splitting your data set into train, test, doing cross-validation, using a whole bunch of different models. We saw ensembles, right? We saw a few different kinds of ensembles. Scikit-learn has a few more. For any sort of model that we look at, scikit-learn has the industrial strength version of that implemented in it. Of course, you're not going to use that for any of your homeworks. You can use it for maybe one of your project submissions. But it's worth getting comfortable with this library because it's almost like the de facto standard for a lot of pre-processing, evaluation. I believe, I'm not 100% sure on this, I believe Kaggle internally uses scikit-learn's F1 score, for instance, to evaluate your submissions. It's a useful library to get familiar with. And we're going to have a tutorial on that. It's a big Python library. Realistically, there is no way 1 hour, 20 minutes is going to cover everything. So the goal of this tutorial will be to primarily acquaint you with it, get you familiar with its style of functioning, maybe walk through one or maybe two example applications. And importantly, all of this will be done inside a Jupyter Notebook or Google Colab. So one thing you can do is you can actually you can bring the laptop and follow along. Nobody learns how to write code by watching someone else write code. So you can bring your laptop and follow along and get comfortable with this. Okay, so that's the plan for Thursday. Any questions about the homework? Or I recognize the irony of a no programming homework being associated with a programming tutorial, but that's the nature of this field. Questions? Yes.
Not related to these announcements, but what's the status on the midterm?
We are working through it. Fulbir is laughing. I don't know why, because we are actually working through it. But yes, I'm hoping that we'll be done in a week. Definitely not going to be done before Thursday.
That's fine.
Yes. Other questions? Okay, so there are no questions. Let's jump back into support vector machines. In the last lecture, we were looking at support vector machines, and the goal of the lecture was to introduce this idea of training a linear classifier by maximizing the margin. And to motivate this, I pointed out that usually, what computational learning theory tells us is a concept class that has lower VC dimension if it overfits a training set, let me repeat that. If a concept class with the lower DVC dimension overfits a training set, then its generalization error is likely to be small. But if a concept class with a large VC dimension overfits a training set, then its generalization error can be large. So lower VC dimension is a better thing. That was the first point. The second point that I mentioned was this idea that all linear classifiers seem to have the same VC dimension. If you have D features, then a linear classifier with D feature in that instance space has a VC dimension of D plus 1. So what does a lower or a higher VC dimension even mean with linear classifiers? Then I pointed you to this example with these two hyperplanes on the exact same data set. Both of them perfectly classify the data, and somehow intuitively there was this agreement that H2 is a better classifier. H2 is likely to generalize better because there's a bigger gap on either side of the hyperplane before it hits any example. This gap here is the margin. The distance to the closest example is the margin. There's a larger margin, and the intuition was that a larger margin is going to generalize better. So clearly, VC dimension did not capture, or at least the version that we saw, did not capture this concept that having a larger margin will generalize better. Well, it did not capture that until we came to this theorem of Vapnik. If we have a set of hyperplanes H, all of these are linear classifiers, but it's not the set of all possible linear classifiers. Given a data set, it's the set of linear classifiers that perfectly separate the data with a certain margin, at least gamma. So Vapnik was able to prove that its VC dimension is the minimum of R square over gamma square, or the dimensionality plus 1. The important point here is gamma is in the denominator. So the margins in the denominator, if you have a set of hyperplanes, imagine you have two sets of functions. H1, capital H1 is a set of functions that has a margin gamma 1, and H2 is a set of functions that has a margin gamma 2. Two sets of linear classifiers, all of H1 has a margin gamma 1, all the functions in H2 has a margin gamma 2. What this theorem tells us is if gamma 1 is bigger than gamma 2, then the VC dimension of H1 is going to be smaller. Larger margin leads to lower VC dimension. And we know from everything that we talked about with learning theory, lower VC dimension gives you better generalization. So larger margin gives you better generalization. And that motivates everything that we are going to do today. That motivates the plan for support vector machines. Instead of finding any linear classifier that separates the data, which is what perceptron did, right? As long as it separated the data, the perceptron stops updating. Instead of finding any linear classifier, let's find a linear classifier that tries to maximize the margin. If you maximize the margin, you lower the VC dimension. If you lower the VC dimension, you have a better chance of generalizing. That's the learning strategy that we are going to operationalize today. Any questions about this plan? Or any questions about how we got here? Two heads nodding yes, three, okay. So that's a good representative sample. So let's now take that sort of somewhat vague idea that our goal is to maximize the margin and convert it into a mathematical optimization problem that will eventually give us the SVM objective. Today, the plan is to derive the SVM objective. I'm not going to tell you how to solve it. We'll just derive the SVM objective today. We'll stop with that. On Thursday, you'll do your tutorial. Next Tuesday, we'll look at how to solve the optimization problem. And the cool thing is that solution strategy for solving the SVM optimization problem is basically going to generalize for other classes of functions like logistic regression. It turns out perceptron's doing that too. It turns out every neural network that you will ever train will also do the same thing. It's essentially a template for solving these kinds of optimization problems. It just so happens that you're going to be introduced to the template through the SVM objective. Okay, so I'm jumping ahead of myself here. Let's now look at the SVM objective. Just to kind of make sure that we are on the same page. We know from learning theory that lower VC dimension leads to better generalization. And Wapnick pointed out that for linear classifiers, the VC dimension depends inversely on the margin. So larger margin leads to better generalization. Incidentally, the V in VC dimension is the same as this Wapnick. So he's done important things in machine learning. To get started, I want to kind of revisit this thing that we've already seen before. The geometry of a linear classifier. A linear classifier in 2 dimensions draws a line on a plane. Let's now work with the assumption that our data set is linearly separable. We'll come back to that later. So if you have a separable data set, you have a linear classifier that basically puts a line in between the pluses and the minuses. And if you have 2 features, x1, x2, you have 3 weights, w1 associated with x1, w2 associated with x2, and b, which is not associated with any feature, it's the bias term. And for any example, x1, x2, in this case, x1, x2, but in higher dimensions, it will be a vector x. You take the dot product of the weights and the features, w1, x1 plus w2, x2, and if there are more, you keep adding them, plus you add the bias term. And so you get this thing inside here. I'll call that the score. I'll give it a better name. So for now, let's just call it the score. And you have a score associated with that example. If that score is positive, you predict positive. If that score is negative, you predict negative. So all positive examples will have a positive score. The margin of this, first of all, the equation of this line is nothing but w1x1 plus w2x2 plus b equals 0. This should not be very surprising. The margin of this data set is defined by the point that is lying closest to this line. It's defined by this point here. It's the distance of that point from the line. We know how to calculate the distance of a point from a line. It's simply the absolute value. In here I have it in 2 dimensions. It's absolute value of w1x1 plus w2x2 plus b divided by the square root of w1 square and w2 square, the norm of the weight vector. This is in 2 dimensions. This expression should look familiar to you. I think homework 0 also brought this up. And in higher dimensions, it's really the absolute value of w transpose x plus b, let's throw in a b here, divided by the norm of w. That's in the 2-dimensional version of that is this thing here. Yes.
Why is there a y in that second equation where it's equals?
Excellent question. Why is there a y? Can you or someone else answer that?
Because y is the true label.
Y is the true label. That's right. We have an example, x comma y. So let's say that this is some x. Oh, you know what? Let's take that example that we were worrying about. This one here is x and the label is +1. And for this one here, it is some, let's call this x1 and this is x2 and -1. I realize I already have an x1 and x2, so I'll call this x prime. What happens if you do not have that y and get rid of the absolute value? You're nodding your head, but I want you to say it aloud.
If you don't have the y and you get rid of the absolute value, then you can get like a negative margin. Or
You get a negative distance. That makes no sense, right? So remember, The score, this is a perfect separator. For positive examples, it's going to give W transpose X plus B is positive. For negative examples, it's going to give W transpose X plus B is negative. If it's positive, the absolute value is exactly that value there, W transpose X plus B. We don't need the absolute value. It's equivalent to saying I'm multiplying by +1. But +1 is exactly the label for a positive example. If it was a negative example, then like this example here, W transpose X prime plus B is going to be negative. But we want the distance. The distance is a positive number. So you need to multiply by -1. But hey, look, we have a -1, the label. So we might as well just multiply by Y times W transpose X plus B. So this quantity here is exactly the same as Y times W transpose X plus B divided by the norm of W. If the numerator was positive, or if the score was positive, you multiply by +1. If the score is negative, you multiply by -1. This is just a interesting way of taking an absolute value using the label. Yes.
Any reason we would prefer one representation over the other?
Yes. Absolute value is not going to be is an inconvenient function. Y times W transpose X is something that you've already seen before. You've seen that in perceptron, right? You want that quantity to be always positive. That YW transpose X is an expression that we are going to keep coming to again and again. We see that here, we'll see that in logistic regression, we saw that in perceptron. And it's an expression that is really, that quantity we would like to keep positive. That's the goal of learning. Yes.
This equivalence is only true since it's linearly separate, right?
Absolutely, yes. This is true for two reasons. One, the data is linearly separable, and two, this particular separator separates the data. So it's not just that it's linearly separable. Imagine that it's linearly separable and I use this line here. No longer true. So it applies only for a separator that's perfect. Okay. So we can measure the margin of the data. How do you measure the margin of the data? You know how to calculate. I'm going to erase some of the stuff here unless there are questions. Let's erase this. So the way I want to calculate the margin of this data is the margin is simply the distance of the closest point to this line. I have a finite number of points. So I can do the naive thing where I have a big for loop, iterate over every single point, compute the distance, and find the thing that's the closest. The smallest value of this quantity here. That's the margin of the data. And the margin, it turns out, is defined by this point here. And when I drew this picture, I intended it to be also defined by any of those 3 points. Okay? But notice that there's something, the weight vector is not fully, is not uniquely defined by these W's and B's. We only care about the magnitude of the W, the magnitude of the score of this quantity here, and not its actual value. If I multiplied the W's and the B's by 1,000, I have the same equation of the line. B plus W1 x1 plus W2 x2 equals 0 is the equation of this line. Equivalently, 1000 B plus 1000 W1 x1 plus 1000 W2 x2 is also the equation of this line. I can multiply by any number. I can divide by any number as long as it's positive. And more important than that, as long as it's positive, the sign of that quantity that I just drew the box around, the sign doesn't change. If B plus W1 x1 plus W2 x2 was positive, 1000 times that is also positive. Half of that is also positive. So we have this flexibility of scaling up and down the weights with a positive number so that we can do something interesting here. Right? Let's just keep that thought in mind because we're going to use that property to do something that is a little bit sneaky. And that part requires a little bit of staring to internalize. But just to quickly summarize what we saw so far, the margin of a hyperplane, the margin of a hyperplane, any hyperplane, is the distance of the closest point from the hyperplane. Among all the points in your data, which are indexed by I, so you have xi with a label yi, the margin of a hyperplane defined entirely by w and b is simply the minimum value among all the data points. This min here is basically a for loop over the data set. You minimize the value of y w transpose x plus b divided by the norm of w. So for this particular hyperplane, we have this value gamma. So far, it's easy, right? I know how to do that. I mean, it might not be the most efficient thing if I implement it as a for loop, but you can think of how to do that. What was the goal of learning? The goal of learning was to maximize the margin. We have this w and b that has this value of the margin. The goal of learning is to find the w and b. So really, our goal of learning is to search among all possible values of w and b and find the maximum value, find the weights and the bias that maximizes gamma. Questions? That search is obviously you can't write a for loop for that because w's and b's are real numbers. Even with floating points, when there's only a finite number of floating points, it's such a large number that you're not going to write a for loop to find the weights and the bias. So we need some other strategy. We'll deal with that later. But conceptually, it is as if you wrote a giant loop over all possible weights and biases. Never do that, by the way, but conceptually, it's like that. And for every one of those, you compute this quantity here. The minimum, the distance to the minimum, the closest point. And then among all the weights and the biases, you find the one that has the highest margin. If you do that, you solve the SVM optimization problem. That's all there is conceptually. Everything after that is actually doing this practically. Just a matter of terminology. Sometimes this quantity here that I defined as the margin, sometimes it's called the geometric margin, and just the numerator alone, yw transpose x plus b, is called the functional margin. I'm not going to really spend too much time, emphasizing this difference because the functional margin and the geometric margin become the same if your weight vector is a unit vector. This is trivia question time. If you go to a trivia game and I don't know where they ask that. Never mind. Let's now go back to. So what I have stated here is formally the goal of training the support vector machine. I've not talked about how to do it, but not just that. I've not even talked about a practical way of getting to this optimization problem because it's non-trivial. So now let's start kind of making this more feasible. The first important point to note is that we don't care about the magnitude of the score. We only care about its sign. So we can scale up and down that number by any positive value, and we have the exact same hyperplane. Right? Yes.
But because we're trying to maximize margin, then we do care about magnitude.
No, we don't, because remember, if you so let's just work this through. Imagine that's a very good question because it's a fantastic segue into the next thing that I want to talk about. Imagine that instead of b, w1, and w2, I have some constant c, some positive number, which we are not going to worry about right now, but let's pretend it's some number. And instead, I'm going to consider b divided by c, w1 divided by c, and w2 divided by c. It seems like these are different weights, right? Now let's calculate the margin of this new set of parameters. you have W1 divided by C x1 plus W2 divided by C x2 plus B divided by C divided by the square root of, so I'll just put a half here, W1 square divided by C square plus W2 square divided by C square. I can, in the denominator, I can pull out a C square common. So I can rewrite the denominator here as 1 over C square times W1 square plus W square, the square root of that, and the square root of this also. But square root of 1 over C square is simply 1 over C, right? So I can just write it this way. And I can pull out a 1 over C common from the numerator as well. Oh, there's an absolute value that I forgot. So I can pull out a 1 over C common, but because C is a positive number, I can actually get it outside the absolute value. So it is 1 divided by C, absolute value of W1 is 1. And now these two get cancelled and we are left with exactly the same thing. All I have done is basically divided the numerator and the denominator by the same value. Why? So it does not change the margin. It's as if, another way to think about it is as if you are zooming in. Imagine that you have a camera and you're zooming in close to the screen versus standing far away from. Just because you, the observer, have moved close to the screen does not change what's happening on the points. Scaling up and down by C is doing something like that. It's not exactly that because of technical reasons, but that's a useful starting point. What's actually happening is the math here. If you do not like what I have written here, I have a cleaned up version. So I can divide the W's and the B by any positive constant C. And I'm going to be left with the same margin. That means what we have is this extra degree of freedom. I can choose C to be 1,000,000. I can choose C to be 10 power minus 1,000,000. As long as it's positive, we have the same weights and the bias. Sorry, it's the same margin. How do I choose the C? We can scale the interesting part here is because I have this extra degree of freedom, if I'm clever about it, I would choose the C, that scaling factor, so that my optimization problem becomes easier. I'm going to solve an optimization problem. I need to solve an optimization problem. If I choose the C carefully, then it turns out that that optimization problem becomes really easy. How do I choose the C? Any positive value of C would work, but here's the sort of non-trivial observation. What if retroactively you go back in time and after finding the closest point, let's say you already found that this is the closest point. Now after finding that this is the closest point, you compute its distance for any weights and bias. Forget about the C for now. Any weights and bias, you compute this distance, and then you choose a value of C so that for that particular point, let's call this point x1, x2. W1 x1 plus W2 x2 plus B, divide everything by C, equals 1. I can choose a C so that that quantity becomes equal to 1. It's a positive number because it's a, oh, well, let's make this, we want Y here, that particular label. That quantity is a positive number, the C. So I can retroactively pick the scaling factor C so that the closest point, for the closest point, the numerator of that margin expression, which, if you remember the trivia I told you, is called the functional margin. The functional margin is exactly equal to 1. If I did that, then for that point and that point alone, this quantity becomes equal to 1, just by construction. If that's equal to 1, then for that point and that point alone, I'm left with just 1 divided by the denominator. Only for that one point. So far, so good? Now, I said I want to learn W1 and W2, right? Instead of learning W1 and W2, what if I automatically, they like by default, try to learn W1 divided by C and W2 divided by C directly? It's just a number, right? W1 divided by C is a number, W2 divided by C is a number. I don't need to have the C lying around. I can just call it U1 and U2. U1 is W1 divided by C. U2 is W2 divided by C. And now my goal of learning is to find that U1 and U2. If I found U1 and U2, then I'm done. I found the margin. But hey, I can't randomly find a U1 and U2. This particular thing is the margin, is the distance of this particular point, the closest point. Can you say anything about the distance of some other point? Let's pick this other point here. With respect to this quantity here, 1 over root of U1 square plus U2 square. Are you sure? What's the definition of the margin? We know that the circled point in this blue, let's call this point A and B. Point A is closer to the hyperplane than B. You already answered, Iris. Say that again.
Distance between A and B.
Let's say I don't want to calculate the distance. I just want a relation between them. Like
It will be larger.
it will be larger. By definition, point A is closer to the hyperplane than point B. That means for the distance, the functional margin of point A is 1. The functional margin of every other point in this data set is going to be more than 1 by construction, because if A is the closest point, every other point should be at a distance, have a functional margin of more than 1 by definition of the margin. So that sets up the learning problem here. Instead of treating the margin as, by the way, I just did a nifty trick here where I called it U1 and U2 here, right? At the bottom. Why do we need to call it U1 and U2? Might as well just call it W1 and W2. These are just names. So I'm going to learn a W1 and W2 such that this quantity here, 1 over square root of W1 square plus W2 square is maximized, but not among all possible choices of W1 and W2, but provided W1 x1 plus W2 x2 plus B is greater than equal to 1 for every point. Why 1? Because we know that 1 is the functional margin of the closest point. Every other point must be further away. Yes.
The type of time around
Uh-huh.
the closest point will change, right?
Yes. And we want to maximize that quantity, which means the place where it gets maximized is in between the pluses and the minuses. Eventually, the SVM objective will find a hyperplane that is exactly in between the pluses and the minuses. Because if you move it around, the closest point, let's take an example here. Let's say I move the hyperplane this way here. So now suddenly this is the closest point. And for that point, we'll be finding a W1 and a W2. The identity of the closest point will change, but this requirement, so this is a plus here, this requirement still stays the same. For the new closest point, we don't care really about we never go around finding the closest point, it turns out. All we need to do is maximize that quantity, 1 over root of W1 square plus W2 square, such that every point has this property. And by doing that, you will end up with a hyperplane. You might be moving this around, but you might end up with a hyperplane that is exactly in the middle of the pluses and the minuses. Because if you move it this way, the point that forms the margin changes and the margin itself changes. We never actually go around figuring out which point forms the margin. We just compute the value of the margin. And that value changes. I've gone through a sequence of somewhat involved tricks here, right? If you've not seen this sort of stuff before, this is not very uncommon in this optimization literature where you play these sorts of tricks to make your optimization problem easier. But if you've not seen this thing before, it may seem a little too clever. So I encourage you to think about it, ask questions if you have any right now. If not, think about it and come with questions. I don't expect you to understand it the first time you see it. I did not. It took me a year or two to actually internalize this. Yes.
So our goal of learning now is not learning the weights directly, but instead the weights with respect to the margin points.
Well, no, we will just learn the weights. Eventually, we'll just learn this W1, W2, and B, which is the scaled up version of that, right? But who cares? We've just multiplied by a positive number. We only care about the sign of that prediction.
Okay.
Eventually, if we had W1, W2, and B, and let's say you have W1, W2, and B, and what you tell me is, let's say you're supposed to give me your classifier, and you give me not W1, W2, B, but you give me W1 divide by 10, W2 divide by 10, and B divide by 10. A new point comes in. You make a prediction, I'll make a prediction. It's going to be the same thing because the sign of that quantity is going to be identical. If W1 x1 plus W2 x2 plus B is positive, W1 divide by 10 x1 plus W2 divide by 10 x2 plus B divide by 10 is also positive. So we don't care about the actual value of the weights, we get the same predictor.
Okay.
Yes.
So are we just saying that we want to minimize the quantity in the orange
Yes.
such that the blue portion is true for every single point?
That's exactly right. That's exactly the SVM objective. Well, almost. I'll change that a little bit more once again. Other questions? If you feel this is confusing, I will encourage you to revisit this till you convince yourself that I am not tricking you here. But I'll just quickly summarize what we have here. The margin of the hyperplane originally is the distance of the closest point from the hyperplane, which is iterate over all the data points and find the one that minimizes that quantity. And the goal of learning is to find a hyperplane that maximizes the margin. But because we only care about the sign of, it's not the sign of W and B. This is wrong. It should be the sign of W transpose X plus B. And not the actual value. You have 1 degree of freedom, which is a multiplier that you can have with to each of these W's and B's, and you can choose whatever you want, and you can think of that if you pretend that that multiplier is chosen such that the numerator of this expression here, the numerator here is equal to 1 for the closest point, then maximizing the margin is exactly the same as maximizing 1 over the norm of W. 1 over square root of W1 square plus W2 square. This is in 2 dimensions. In any number of dimensions, this is 1 over norm of W. Just a second. But these two things are equivalent if and only if for every single point, the functional margin or the absolute value of the score is more than 1. The absolute value of every point should be more than 1 because this construction only works if the absolute value of the absolute value of the score is equal to 1 for the closest point. Yes.
So 2 questions. How do we find the closest point, and then also with the perceptron or like our update rule changing our plane?
Effectively. If you're now asking about the algorithmic aspect of things. Sure, this is, if you believe this is correct, how do you actually solve this optimization problem? And that's the algorithmic part that we'll talk about next Tuesday. Essentially, I'll give you the short answer. We'll be using stochastic gradient descent. And once you start looking at stochastic gradient descent and staring at the algorithm for a support vector machine, you'll see that the actual implementation is maybe about 2 lines of code different from perceptron, which is just amazing. I mean, every time I see that, I feel so satisfied because that means that there's something fundamentally right about it. But we'll come there next week. Yes.
So why this, like, unstable, like, more issue or better than the original one?
The original one was, well, first of all, nothing can be worse than the original one, which is a big for loop over an infinite set. It turns out this particular setting, maximizing, okay, you know what? Let me write this up. So the problem is to maximize over all W and B 1 over the norm of W, such that for every point that is in the data set, y times yi W transpose xi is greater than or equal to 1. If you've not seen this notation here before, this stands for such that it's just, this is a constrained optimization problem. I want to maximize 1 over norm of W. Maximizing 1 over norm of W is equivalent to minimizing the norm of W, such that the same constraint holds. Minimizing the norm of W is equivalent to minimizing the squared norm of W. Now, it might seem like I'm just playing games here, but we've arrived at something interesting here. This squared norm of W, if you have a weight vector, W1, let's just take 2 dimensions, W1 and W2. This is your vector. Its norm is the square root of W1 square plus W2 square. The norm of this vector is this thing here. The squared norm is simply the sum of Wi square for all the weights. So I'm minimizing this. Oh, by the way, if I have Wi square, this is exactly the same as W transpose W. I take the dot product of a vector with itself, I get a squared norm. Once again, I've not done anything interesting here. I've just I'm playing with these symbols. Maximizing 1 over W, norm of W is exactly the same as minimizing the norm of W, which is exactly the same as minimizing the squared norm of W. But the squared norm of W is simply the dot product of W with itself. And just for good measure, I'm going to put a half here. Well, I have this, and I've not told you that this is any better or simpler. It just seems like different. Turns out this is actually better. And the reason for that is, so we have this learning problem here. Now, this particular learning problem is an instance of a very well-studied family of optimization problems called quadratic programming. Is anyone taking optimization in the math department? I know there's at least 1 or 2 people in the class who are doing that. Basically, quadratic programming is extremely well studied in the optimization community. This is, in some sense, like a homework problem. So when SVM was first introduced, what happened was the goal of learning all this VC dimension and all that was used to motivate this problem. And then eventually, when you're able to write down the optimization problem as an instance of a quadratic program, QP, at that point, for some people, problem solved. Because it's no longer their problem, it's the problem of these optimization people. That's what they do for a living. might as well make it their problem. Almost. It turns out that this particular quadratic program has a very nice structure that you can do much better than the standard techniques that are used for quadratic programming. We'll talk about that, and that's why we can do stochastic gradient descent. But the reason why this is interesting, our original goal was to maximize there's an expression that's the margin there. I don't know why. Oh. Our original goal was to maximize the margin, which is a rather ugly expression with square roots and stuff like that. Now we just have a quadratic objective. We want to minimize a quadratic objective subject to linear constraints. That's a very special problem structure that is well studied. But even before we go into how to solve this problem, let's look at this objective a little bit more. Let's look at this learning problem. It has an objective and some constraints. The objective says minimize the norm of half the norm of W. Minimizing half the norm of W is equivalent to maximizing 1 over the norm of W, and that is equivalent to saying I want to maximize the margin such that the closest point has a functional margin of exactly 1. And every other point, xi, yi, every point, if you include the closest point, has a functional margin of at least 1. So y w transpose x, notice that I got rid of the b here because I was getting bored of writing b. Really, this should have been yi w transpose xi plus b. 1. But from now on, I'm going to assume that your bias is now a feature and it's folded into the weights like we used to do before. Yes.
Is the constraint, where do we represent the constraint that the closest point's norm is 1? Like
Here.
what portion is, where is that represented?
There, right there. It's the thing is, the fact that this is greater than equal to makes 1 the closest. Every point, for every point, let's ignore the greater than equal to for now. Let's make it strictly greater. Let's pretend that there's exactly 1 point that forms the margin. For every single point that's not that point, yw transpose x should be more than 1. If you include the point here, then it should be greater than or equal to 1. Other questions? Yes.
It's not super clear to me what or how we're getting 1. All right, so 1 is a measure of distance.
It's not a distance really, it is this, it's simply the numerator of this expression here that is set to exactly 1. It's that expression, it's that expression computed on the closest point. If you choose your scaling factor so that that expression on the closest point becomes equal to 1, then by definition, because it's the closest point, for every point that's not A, that quantity should be more than 1. And you choose your C carefully. You choose your scaling term carefully. It's not a distance because you're not normalizing it. Which is why in some places it's called the functional margins, not the geometric margin, which is the distance. I thought I saw another hand go up, but sure. Okay. This optimization problem is called the hard support vector machine. It's not hard because it's difficult. We'll talk about that in a bit. But I'm not going to tell you how to solve this optimization problem. Because let's, at least today, pretend it's somebody else's problem. It's Tuesday's problem, next Tuesday's problem. Today, we are just defining the optimization problem. This is called the hard support vector machine, but let's just recap how we got here. So far, We started off with this idea that lower VC dimension gives better generalization. And then Vapnik comes along and says the VC dimension of a linear separator with margin gamma is inversely proportional to that margin. So larger margins leads to lower VC dimension, which leads to better generalization. For the separable data set, or if you know your data set is separable linearly, then you want to find the classifier that maximizes the margin among all the classifiers that perfectly separate the data. That there are, if you have a separable data set, there are an infinite number of linear separators that perfectly separate the data. And you want to find the one separator that perfectly, that maximizes the margin. And we just went through this rather involved argument that said maximizing the margin is equivalent to minimizing W transpose W, provided for every example, Y W transpose X is greater than or equal to 1. And that set up an optimization problem. Why is this not going to work? When will this fail? Or let me ask you a different question, the same question slightly differently. Let's say that I implemented this learning algorithm and your job is to break it. Your job is to make my algorithm throw an exception. Yes. That's right. I assumed that it's separable among all hyperplanes that perfectly separate the data. You can do all of this. If you know your data is linearly separable, you're in a very good place. Most of us don't have that luxury. So how do we address that problem? If your data set is not separable, so what do you do? By the way, this is called hard SVM because it assumes hard separation. It's not hard SVM because this is difficult. So what happens to your hard SVM objective if your data is not linearly separable? Where does this fail? Yes. So the answer is on the condition yi W transpose xi should be greater than or equal to 1. Can you say why? So in fact, that's basically yi W transpose xi being strictly greater than 0 is a requirement for linear separability. Strictly greater than 0 is greater than or equal to some positive number, right? Any positive number, it turns out. You can pick any positive number, you might as well choose 1. So if your data set is not linearly separable, this condition, right, that for every single example, yi W transpose xi should be greater than or equal to 1, will fail, at least on one example. What that means is, let's think about what this for all means. For example number 1, y1 W transpose x1 should be greater than or equal to 1. And for example number 2, y2 W transpose x2 should be greater than or equal to 1. And so on. For every single example. Let's say you have a weight vector where this part does not work. You want an AND of all of these things, that means the entire set is false. So your condition fails. Among all linear separators that satisfy the condition, your job is to find the one that has the minimum norm. Among all linear separators that satisfy the condition, you're left with an empty set. Out of an empty set, find the one that has the smallest value. That's not a meaningful optimization problem. So the hard SVM, if you give it to if you give a data set that's not linearly separable to it, the constraints form an infeasible set. It's an infeasible problem. That means there's no solution. If you think in programming terms, this is equivalent to an exception. You are giving an empty set and asking, find the minimum value. That problem is not defined. Because why is it an empty set? Because there's no hyperplane that satisfies this inequality for every single example, because the data is not linearly separable. How do you deal with not inseparable data? Any ideas? Yeah.
You could represent the data in a new representation.
You could do that. You could do that for sure. And let's say we don't do that. Let's say we want to live in the same representation. How do you, any ideas? Any other ideas? Yes.
Acceptable losses,
What do you mean by that?
like almost like a margin, another margin of error, like the amount that you can go off.
So this is almost the same answer as what's on Zoom. You could use an additional margin like you did for margin perceptron. You're allowing this gap, this sort of a fudge factor. I'll give you a slightly cleaner version of that answer. Let's say you have a data set like this. There's this one example that's clearly in the wrong place. The minus is in between the pluses. If you got rid of that example, suddenly the data becomes linearly separable. Maybe we should allow that example to be, we should ignore that example. Your data becomes linearly separable. Seems like a reasonable answer. I mean, it seems like an answer that will work. Whether it's reasonable or not, we'll come to that later. It seems like an answer that will work because if you ignore that example, let's pretend that the highlighted example is not there, then you draw a line here, you get a perfect separator. And then you can go back to the same game that we had. Train the SVM. We are back in the hard SVM case. Well, you know what? As long as we are ignoring examples, why not ignore this example also? Because if we do that, the original data had a margin of this much. If we got rid of that plus in the middle, we can draw a nice big hyperplane with a very large margin. Might actually generalize even more. Right? Do you see the downside of this game? While we are ignoring examples, why not ignore all of them? Throw a hyperplane anywhere on the screen and it gives a perfect margin. It gives a perfect separator with infinite margin. Must generalize so well. So this is a trade-off, right? You can choose to ignore examples and you can solve the optimization problem, but then you're actually ignoring data. You are underfitting the original data. That's basically what we're going to do though. Let's say we draw this hyperplane and we start getting rid of examples. If we do that, this separator here has a large enough margin that it's going to generalize well, but at the cost of actually ignoring examples. So maybe you're missing out on some signal. So there's a trade-off here. On one hand, the whole VC dimension story says this hyperplane will generalize well. On the other hand, by ignoring examples, you're ignoring examples. You're losing signal that can lead to the classifier underperforming. So there's one force that pushes the classifier to do well, generalization. There's another force that pushes the classifier to do poorly because you are underfitting the original data. Maybe what we need is a hyperparameter that says, I need to balance these two things. Ignore the examples, but not too much. And how do we find that good hyperparameter? Through cross-validation. That's going to be the game we'll play for the next 10 minutes. Everything that I just said, let's now make it a little bit more formal than just say, I'm going to toss out one example at a time and see if it works. So we're going to set up a system that allows us to compute a margin only using examples on which are not ignored. Originally, we started off with this hard SVM where we're trying to minimize the norm of the weights such that for every single example, YW transpose X is greater than or equal to 1. For every example, I'm going to give it the opportunity to break into this margin, like these examples here. All of this side should be plus. And ideally, we want the examples to lie outside the margin. This example here has broken into the margin in the wrong side, this to this by this much amount. Really not that much amount. Actually, that minus should have been somewhere here. So it has actually gone from all the way from here to here. The plus, I've allowed it into the margin by going this much. Right? In a perfect world, all the minuses are here and all the pluses are here. This one bad minus, I have given it the freedom to travel all the way to the wrong side. And the one bad plus, I have allowed it to break into the margin. And by doing that, I'm working with a hyperplane that has a larger margin. So this distance here, right? That's called a slack. I'm going to introduce a slack variable for every single example. I'm going to allow every single example the opportunity to break into the margin just like this plus and the minus did. So I'll introduce one slack variable for every example. What does it mean to say that it's going to break into the margin? Instead of demanding that YW transpose X should be more than 1, I'm asking YW transpose X should be more than 1 minus the slack. The slack here is the Greek letter xi, xi, and I have been writing this Greek letter for about 15 years now. I still don't know how to write it. So when you see me do this, that's a psi. That's my best approximation of a psi. So for every single example, I introduce a slack variable psi, which is to be interpreted as how much is that example allowed to break into the margin. Breaking into the margin is essentially the same as saying, instead of the functional margin being at least 1, the functional margin should be at least 1 minus psi I. We have a new optimization problem now. The intuition is the slack variable allows every example the opportunity to break into the margin. And if the slack variable is 0, then the example is either on the margin or on the correct side of the margin. The slack variable being 0 means it takes us back to this setting for that one example. So it's that example is doing okay. If the slack variable is positive, that means the example has broken into the margin. And all slack variables have to be either 0 or greater than 0 by construction, by definition here. So we have a new optimization problem. We have the same objective, W transpose W. For every example, I want it to be able to break into the margin by saying YW transpose X should be more than 1 minus psi I. This is that picture that I just showed you. And there's this extra term in the objective. You know what? If I allow every example to break into the margin, then there's a trivial answer here, which is I'm going to set psi I to be negative infinity. So let's pretend that the shaded thing does not exist. Let's pretend that this does not exist for now. Then what I'll do is, if all I have to do is minimize the norm of W such that YW transpose X should be greater than or equal to 1 minus psi I, and the sides have to be positive, then I will set every single side to be infinity, not negative, just infinity. By setting it to be infinity, this quantity becomes minus infinity. YW transpose X is going to be greater than minus infinity. I don't really care about the W and the B. Just pick a random weight vector. Well, we can't pick a random weight vector because I need to still minimize norm of W. What values of W minimizes W square? 0. So if you do not have that thing that's crossed out, then the trivial solution to this is set all the weights to 0 and set all the slacks to infinite. What that means is setting the slack to infinite means for every example is equivalent to saying every single example breaks into the margin on the wrong side. Or equivalently, every single example gets tossed out. We have a data set, we ignore the data set, and then return the weight vector 0. Weight vector equals 0 means if W is the 0 vector, That means W transpose W is 0. That means 1 over W transpose W is infinity. It has an infinite margin. On all the 0 examples that are left behind, we have a weight vector that has an infinite margin. It's amazing. The maximum margin possible on no data. This setting is set to underfit the data. It basically ignores the data. And to control for that, we can't allow the size to become arbitrarily large. So we have this extra term here. This quantity here says, while you're minimizing the norm of the weights, also minimize the sum of the size. It says, do not make the psi very large. Don't ignore every example, only ignore the examples that you really need to ignore. This gives us the full optimization problem. I call this the soft SVM just to contrast it against hard. Nobody calls it that. This is just the SVM. This is the support vector machine. Yes,
What is the C term?
I'll come to that in a minute. So let's stare at this objective and see if we can understand this a little better. There's this term that says minimize half W transpose W. I notice nobody asked me why I have a half. Because I'm going to take a derivative of that. The derivative of W square is 2W, and the half cancels out the 2. And that means that I will have fewer bugs in my code later on when I forget to put the 2. So the objective is to the thing inside the box maximizes the margin. Plus the sum of the size, which is essentially saying minimize the total slack. Allow as few examples as possible to violate this margin constraint. And even if they do, don't make them too far on the wrong side. That's what minimizing the sum of the slack, the total slack does. And then the constraints remain the same. C is a trade-off term. The term C is essentially saying, how much do you want to generalize? Maximizing the margin, generalize this, versus how much do you want to ignore the examples? If imagine that C equals infinity, C should be a positive number. Imagine that C is infinity. If C is infinity, what that says is the only way in which you can do anything to this expression is if you set this quantity to be 0. Because any real number, any positive number psi, will immediately make this objective infinite. So the only hope you have is to set the sum of the size to be infinite, set the sum of the psi to be 0. If C equals infinity, that means every single psi should be 0. That means this thing goes away because every psi is 0. That means we're back to the hard SVM. C equals infinity is the same as hard SVM. Or alternatively, C equals infinity is demanding that you must perfectly separate the data using your linear classifier. More generally, as C gets larger, you are demanding that your learner overfit the data. You need to perfectly explain the entire data. As C gets smaller, you're saying, I'm okay allowing the second term is less important in this objective. So go ahead, ignore the examples, ignore more examples. As C gets smaller, you are essentially underfitting the data. You're ignoring examples, which means you're underfitting the data. So C is really a trade-off parameter that controls between overfitting and underfitting in this objective here. That's the answer to your question. So let's take stock of where we are. We started off with lower VC dimension being better generalization, and Vapnik comes along and says maximizing the margin is better for generalization. For the separable case, we set up an optimization problem that said, among all linear classifiers that perfectly separate the data, find the one that maximizes the margin, which is exactly the same as find the weight vector that minimizes W transpose W, provided for every example, YW transpose X is greater than or equal to 1. But that has the problem that it assumes your data set is linearly separable. We want to work with real data. And the answer is you introduce slack variables, which allow examples to violate the margin condition by working on that right-hand side of that expression. And you minimize the slack in addition to maximizing the margin. And that's your full optimization problem here. Any questions about this? And then I'm going to show a different version of this optimization problem, which is the one that we'll stop with. But I mean, that's the one that I will call the SVM objective. Any questions about what we've seen so far? Everything that we've seen so far might be a little too detailed and complicated. Even if you feel like it makes perfect sense, I encourage you to go back and revisit this because nobody learns math by watching someone else talk about math. You need to kind of, feel it, whatever that means. Um, it turns out this expression can be simplified. Yes.
You said you find the best slack variable for cross validation.
No. You notice that I have put both W and psi inside the objective. Just like your optimization, your optimizer is optimizing for the W, it's also going to optimize for the slack. The only thing you find by cross-validation is the C, a single number. Because if you have to cross-validate over all possible slack variables, if you have 100 examples, then you need to consider 100 real numbers. Slacks are real numbers, positive numbers. It might as well make it a learning problem at that stage. Actually, you know what? I'm going to rewrite this objective and get rid of the slack variables entirely. Because notice that, let's focus on these two expressions. The bottom one says psi I is greater than or equal to 0. The top one, if I move the psi to the left and the y w transpose x to the right, I get psi I is greater than or equal to 1 minus yi w transpose xi. The psi I should be greater than 0, and it should be greater than this the 1 minus yw transpose x, which means it should be bigger than the larger of those two things. So I might as well say psi I should be greater than, oh, I should not have erased that. It should be greater than 0, and it should be greater than 1 minus yw transpose x. So it should be greater than the bigger of those two things. For technical reasons that I don't want to necessarily go into, it turns out you can take this thing here and directly, or rather this thing here, and directly plug it into this part here. So you'll be left with an optimization problem that has no constraints. Minimize half W transpose X, W plus C times the sum over every example, max of 0, 1 minus YW transpose X. We've gotten rid of all the constraints by plugging in that inequality. It's not the exact same optimization problem, but it turns out these two optimization problems have the same solution. This form is far more interpretable, and whenever I say SVM, this is the thing I mean. Let's examine this objective. It has two terms. It has no constraint, importantly. It has two terms. The term on the left says minimize W transpose W. Minimizing W transpose W is equivalent to maximizing the margin. The second term has a summation over the entire data set. And to answer the earlier question, how do we find the slack? Well, there's no slack anymore. This summation is over the entire data set. For every single example, you compute this quantity. And it turns out you can interpret that quantity as a penalty for making a prediction using this weight vector W. Let's look at three cases here. Case number one is, let's say the example is correctly classified by this weight vector. Imagine that we are sitting on a certain weight vector and we would like to know how good it is. So this weight vector perfectly classifies an example And not only that, it also puts it outside the margin. That means for that example, yi w transpose xi is greater than or equal to 1 by definition. That means 1 minus yi w transpose xi is less than or equal to 0. The max of 0 and a negative number is 0. So the penalty for making a prediction on a correctly classified example that's outside the margin is exactly 0. Let's consider the next case. The example is incorrectly classified. That means yi w transpose xi is less than 0. We know this, right? Because if y w transpose x is negative, there's a mistake. This is what you saw for perceptron also. If y w transpose x is less than 0, that means it's clearly less than 1. That means 1 minus yi w transpose xi is greater than 0. This quantity is bigger than 0. That means the max is 1 minus y w transpose x, which is a positive number. So that's the penalty. So the weight vector has incorrectly classified the example xi yi. So it gets a penalty of 1 minus y w transpose x. Let's look at the third case, which is the more interesting one. The example is correctly classified, which means yi w transpose xi is greater than or equal to 0. But it's not crossing the margin threshold, which means it's less than or equal to 1. It's placed within the margin. It's like that plus that we had. It was on the right side of the hyperplane, but inside the margin. That means 1 minus yi w transpose xi is a positive number. 1 minus yi w transpose xi is positive, which means the max of 0 and that is that quantity. Even though this weight vector assigns the correct label to this example, because it puts that example inside the margin, that weight vector gets a penalty. And that penalty is exactly how bad it is, 1 minus yw transpose x. This expression, max of 0, 1 minus yw transpose x, has a name. It's called the hinge loss. The hinge loss is simply given an example xy and a weight vector w, penalize the weights according to this scheme. Correct prediction outside the margin, no penalty. Everything else gets a penalty. Even if the example is correctly predicted, it gets a small penalty because it's inside the margin. You can visualize this, and that's the last thing we'll do today. The original goal of learning is to, if the horizontal axis is yw transpose x, the vertical axis is the penalty, number of points you lose for making a certain prediction. If yw transpose x is positive, that means there's no penalty. If yw transpose x is negative, that means there is a penalty. That's your 0-1 loss. It's called the 0-1 loss, which says you lose a point if you make a mistake. You lose nothing if you don't make a mistake. The hinge loss says the 0-1 loss is just basically the number of points you lose for making mistakes. 0-1 loss is not differentiable. The hinge loss assigns a penalty based on the margin. You have this 1 here. If there is no mistake and the example is far away from this margin of 1, there's no penalty. If there is a mistake and the example is on the wrong side, you keep getting a penalty that grows the more you put the example on the wrong side. Even a correctly predicted example that's placed within the margin gets a penalty. So if an example is placed here, it gets a penalty of that much. And those are the 3 cases that we have here. All right, I'll stop here now. We've talked about SVM. We've talked about this loss this idea of the hinge loss. On Thursday, we'll be looking at the tutorial. On Tuesday, again, we'll look at how to solve this optimization problem. But before that, I'll point out we've actually uncovered a very important idea in machine learning, which is to take the question of learning and making it somebody else's problem, making it an optimization problem. And that's the most dominant strategy for machine learning today. And we'll be kind of living that world for the rest of the semester. All right, I'll see you in the next lecture.